Our topic today is photoelectric effect. That's what we want to discuss in this lesson. Now, when we talk of photoelectric effect, as you can see, the word photo here means light, and electric from electrons or even electricity. And therefore, we want to see the effect of light on the flow of electrons when they fall on a metal surface. Now, class, when an electromagnetic radiation of sufficient frequency is radiated on a metal surface, electrons are emitted. Let me put that on writing. When an electromagnetic radiation of sufficient frequency falls on a metal surface, electrons are emitted. When it radiates a metal surface, then electrons are going to be emitted from this metal surface. Now, we are saying that these electrons are now called photoelectrons. These electrons are called photoelectrons. The electrons that are emitted from a metal surface when a radiation of sufficient frequency falls on a metal surface, we call them photoelectrons. Now, what is this that we call photoelectric effect? Let's also define this. So when we talk about photoelectric effects, just like we have said above, that when a radiation, an electromagnetic radiation of sufficient frequency falls on a metal surface, then electrons are going to be emitted. These electrons are called photoelectrons. Now, when we talk of photoelectric effects, here we are referring to a phenomenon in which when light or radiation of sufficient frequency falls on a metal surface, electrons are emitted. So, photoelectric effect is a phenomenon. This is a phenomenon in which when light or radiation of sufficient frequency falls on a metal surface, electrons are emitted. So class, if you are asked to explain or rather define photoelectric effect, simply say that this is a phenomenon in which when light or radiation of sufficient frequency falls on a metal surface, electrons are emitted, and these electrons, we have said that they are called photoelectrons. Now, those materials that exhibit photoelectric effect, we refer to them as photoemissive. So, materials that exhibit photoelectric effect are said to be photoemissive. So a photoemissive material is that material that when radiated with a radiation or light of sufficient frequency, this material is capable of emitting electrons. That material we call it photoemissive. Now we want to demonstrate photoelectric effects. Demonstrating photoelectric effects. Photoelectric effects. We are going to demonstrate this one in two cases. The first case being using neutral plates. Using neutral plates. And in using these neutral plates, I want to use some two metal plates. We will also use a power source, galvanometer, and even connecting wires, and a glass plate, which is a barrier, which is going to, in a circuit now, we may have it appearing this way. So that we have a galvanometer and so the radiations are directed to this plate. This is plate A, this is plate B. In that particular circuit, as you can see, this is the UV radiation. UV radiation. Now the UV radiation are ultraviolet radiations which are emitted by the sun. So as the plate A and we have plate B the other side, and when these are called metal plates because they are actual metals, metal plates, and this is a galvanometer. The galvanometer has got center zero pointer, which is going to actually reflect whenever current is going to flow through this particular circuit. Now, what is happening here? What do you think will be the observation when now we direct the UV radiation onto metal plate A? Now, if you direct this UV radiation onto metal plate A, the observation will be that the galvanometer is going to deflect. Now, what do you think will make this particular galvanometer to deflect when this UV radiation falls on a metal plate A? Now, we are saying that when this UV radiation falls on metal plate A, what happens is that electrons are going to be emitted from metal plate A, which is actually connected to the negative terminal of the cell, as you can see here. Now plate B is connected to the positive terminal of the cell, and therefore it is taken to be positive. Remember, class, that electrons are negatively charged, and therefore when they are emitted from the plate A, which is negative, they will be attracted towards metal plate B as they flow. That current, we call it photocurrent. Now the current that flows through this particular circuit is the one that makes this galvanometer to deflect. Now we are saying this, let me put that one, the observation here, that we have said that the galvanometer deflects, right? Galvanometer deflects. That is, which now will cause the current to flow through this particular circuit, making or causing the galvanometer to deflect. Now, what will happen if you introduced a glass plate, just a barrier, we call it a barrier, you introduce it here, such that now that barrier blocks these radiations from reaching plate B. What will happen there in that case, class, is that the glass plate will block these radiations from hitting metal plate A, and therefore no photoelectrons that will be introduced. As a result, there will be no no deflection on the galvanometer. That's what you're saying there. So if a glass barrier is introduced between the plate A and the UV radiations, no deflection will be observed on the galvanometer. And I think last I will explain the reason as to why this will happen. So I have said that when the UV radiation hits plate A, electrons are not to be emitted from plate A and then get attracted to plate B, causing current to flow through this circuit, hence the deflection of the galvanometer. Now, if we introduce a glass barrier, that's a glass plate, between the two plates, between the UV radiation and the plate A, what happens is that the glass plate will be flowing here, hence no deflection on the galvanometer. That is what you need to understand as far as when we are demonstrating the photoelectric effect using the neutral plates. Now, what do you think? What about when I think class taken that point, and therefore we can now move to part B. Move to part B using charged electroscope. Using charged electroscope. Now, in this case, of course, the apparatus will include the what we call electroscope to illustrate what we have in this case. So, let me have this one. This is the rotary electroscope. So this is a positively charged electroscope. We want to see the effects of the electric effect on this electroscope, which is charged. Now, this is a mercury vapor lamp. UV radiations. And this is a brass cap. And this one here is called zinc plate. So this one is also equally positive charges. These are positive charges here. So this is a positively charged electroscope. Now, suppose we have now a negatively charged electroscope. We will also have a similar diagram on this side. So, UV radiations, zinc plate, so part B, negatively charged electroscope. So class, you can make some observation regarding these two diagrams that I've drawn here. You realize that when we are using a positively charged electroscope, there is rise in leaf divergency. You know, it was initially charged. We are using charged electroscope, so that means initially the leaf actually had there was leaf divergency, and even after the UV radiations now falls on this zinc plate, still leaf divergence will have remained the same. So in that case, leaf does not fall. Leaf does not fall. But here, it was initially charged, so that means there was leaf divergency. But after the photoelectric emission has taken place, what happens is that the leaf now falls. In this case, leaf falls. So we want to know why the leaf remains the same when using a positively charged electroscope and leaf falls when we are using a negatively charged electroscope. Now, now what we are saying here is that when this UV radiation is directed onto the zinc plate that is connected to a positively charged electroscope, when it falls here, then what happens is that the leaf divergence here on the positively charged electroscope, the leaf divergence remains the same. It does not fall. But when we are using a negatively charged electroscope, initially there was leaf divergence, but now when UV radiation falls on the zinc plate, the leaf divergence is going to fall, leaf divergence is going to decrease, and I want to know the reason as to why it happens like that. Why it happens like that. So let us have the observation here before we explain. Or regarding the two diagrams that I've just drawn there. So we are saying that for the positively charged electroscope, leaf divergence remains the same. Also, we are saying that for the negatively charged electroscope, leaf divergence decreases. Leaf divergence will decrease. So here, leaf has fallen. There is leaf divergence has decreased, but here leaf divergence actually remains the same. then we need to offer an explanation as to why this one leaf divergence here remains the same, and here on the negative charge electroscope, leaf divergence decreases. So let's try to offer some explanation regarding this observation. Now class, what we are saying here is that for the positively charged electroscope, when the UV radiation falls on the zinc plate, now of course electrons are going to be emitted, but the emitted electrons do not escape. They get attracted by the positive charges on the electroscope. As a result, beam divergence remains the same. That the electrons here are going to be emitted from the zinc plate, but those emitted electrons are not going to escape, but they are going to be attracted by the positive charges on the electroscope, and therefore the beam divergence will remain the same. When it comes to negatively charged electroscope, now we are saying that when the UV radiation now falls on the zinc plate, what happens is that the zinc plate is going to emit electrons. Now the emitted electrons are going to be impaired. They are going to be impaired by the negative charges on the electroscope, and therefore they escape. As a result, charge decreases. The charge on the electroscope is going to decrease, and therefore beam divergence falls. That is what causes what we are seeing there. That is what causes what we are seeing there. So we are saying this: when the radiation, the UV radiation radiates the zinc plate, electrons are emitted, but full stop. The emitted electrons are attracted, do not escape due to the attraction by the positive charges, positive charge on the electroscope. Hence, beam divergence remains the same. That's, we are saying that when the zinc plate is related with the UV radiation, electrons are emitted from the surface. The photoelectrons now emitted from the positive charge of the zinc plate do not escape due to attraction by the positive charges on the plate, and the beam divergence therefore remains the same. Now, what about on the negative charge electroscope? The photoelectrons emitted from the negative charge electroscope are repaired, and the electroscope becomes discharged. As a result, the beam divergence decreases. We are saying that here the photoelectrons emitted from the zinc plate on the negatively charged electroscope the photoelectrons that are emitted from here on the negative charge electroscope are going to be paired. Are repaired. That means, you know, they are going to be, they are emitted and then repaired away, so they get expelled from the electroscope, and therefore they are repaired. Hence, the electroscope get discharged and the leaf falls, and thus the leaf falls. So the electrons emitted here are going to be repelled away, and therefore the electroscope will get discharged. The charges here will decrease, and therefore the leaf is going to fall. That is what causes the decrease in the vacancy on the negatively charged electroscope. Now, what do you think will happen if we used an ordinary glass which is likely to absorb some of these particular radiations, so that you place that particular glass and you place it here in between the mercury vapor lamp that produces the UV radiation and the zinc plate? When you introduce that ordinary glass plate here, that glass plate is going to absorb the radiations, and therefore those radiations are not going to reach the zinc plate to cause the emission of electrons. As a result, there will be no observation, there will be no change in leaf divergency here when we place a glass plate in between the mercury vapor lamp and the zinc plate, because that glass will actually absorb that radiation, causing no photoelectric emission. I think that's also an important point that you need to note. Just like I have said, I think you have noted it down, students, because it's an important point that you need to know. Because you will be asked what will happen if you introduce a glass plate which absorbs the UV radiation between the mercury vapor lamp and the zinc plate. I have said that what will happen there is that there will be no change in leaf divergency, because that glass plate will absorb the UV radiation, and therefore no radiation will reach the zinc plate to cause photoelectric emission. I want us to note this point, that it is important that even before you carry out this experiment, it is important you clean thoroughly this zinc plate. Why do we need to clean it before carrying out this particular experiment? We need to clean it thoroughly so as to ensure that there is maximum emission of photoelectrons. Otherwise, if we use it the way it is before cleaning it, photoelectric effects may not take place. So class, we are saying that the zinc plate need to be cleaned before use to ensure maximum emission of photoelectrons. The reason as to why we need to clean this zinc plate before carrying out this experiment, it is to ensure maximum emission of photoelectrons. Otherwise, if it's not clean, then photoelectric emission may not take place. Now, class, that is how to demonstrate photoelectric emission in photoelectric effects. We want now to turn to light energy and quantum theory. Light energy and quantum theory. light energy, and quantum theory. Now, light is energy itself, and as it travels, this radiation, the UV radiation, is in form of light from the sun, and as it travels from the sun, then it carries some energy with it, and now there is a scientist called Max Planck who came up with an idea that light energy is propagated as small packets of energy. That scientist is called Max Planck. Max Planck came up with an idea that light energy is propagated as small packets of energy. Light energy is propagated as small packets of energy, That this energy, as it travels from the source, it comes in form of packets, small packets of energy. They are propagated in form of small packets of energy. Now, each packet is now what we call the quantum. Each packet is called quantum. Each packet is called quantum, and in plural we call it quanta. When those packets are many, then we refer to them as, or we call them quanta. That's what you're saying there. Now, this amount of energy are called photons. This discrete amount of energy is called photons. Those packets of energy are the ones that we refer to as photons. Now, one photon, that's one packet of energy, can carry a given amount of energy. That's what we want to look at. So we are saying that the energy possessed by a photon is given by a photon is given by E is equals to HF. That energy is equals to HF, where in this case, where H is Planck's constant, and is equivalent to the H now is equal to 6.63 times 10 raised to power negative 34 joules second. H is a constant, and it is called Planck's constant. And the value of Planck's constant H is equal to 6.63 times 10 raised to power negative 34 joules second. Now F is the frequency of radiation. Frequency of radiation. The frequency of that radiation from the source. Now, from the general wave equation we know that wave equation, we have that C is equals to F lambda, where in this case C is the speed or velocity of light in a vacuum. And therefore, from that equation, we can make F the summation of the formula and get that F is equals to now C over lambda. If we substitute, lambda is the wavelength. In this case, lambda is the wavelength of that particular radiation, and the velocity of light in the vacuum. Now the frequency of radiation will be given by this formula, that's E over lambda, and we can substitute this one up there, the equation that we have up there, then we are going to have it as E is equals to now H multiplied by C over lambda, the wavelength. That is how we can also get the energy of photon. Now, this is, you realize that when the wavelength is long, you know that the radiation with a long wavelength will have a small amount of energy, but a radiation with a short wavelength will actually have maximum amount of energy. That is what we need to understand in this particular case. That when this one is maximum, we are saying that E that is radiation with a long wavelength has a low energy. So class, that is what we talked about, and that is what you need to understand as far as the light energy and quantum theory is concerned. So the most important thing is to understand this particular formula and get to know how it comes about. To that point, class, I would like to stop there and usher in. Okay, I want to stop there and then conclude, so that we will pick it up from there in our next class. Thank you so much. Thank you for listening. Okay, I want to appreciate all of you for attending this particular lesson. I want to believe that you have really enjoyed it, and we shall have a next one. I want to invite all of you, please come and enjoy this particular lesson. Otherwise, let me stop here and set you free for other activities. Thank you so much. God bless you.
Now you can
put it live so that I can see myself.